What happens when the most powerful telescope ever built detects a molecule we thought only life could produce, then finds it in a place where life cannot exist? When phosphine appears in the turbulent atmosphere of a dying brown dwarf 54 light-years away, does it confirm our understanding of chemistry or shatter our confidence in searching for alien life? As of November 2025, the James Webb Space Telescope has placed us at a crossroads. Two separate discoveries, phosphine in a failed star and dimethyl sulfide on a potentially habitable exoplanet, have ignited fierce scientific debate. Neither proves life exists beyond Earth. Both force us to ask, do we even know what life's chemical signatures look like? These aren't abstract philosophical questions. They're the frontline battles in humanity's search for cosmic company, fought with infrared spectroscopy and statistical thresholds. This is exactly the kind of deep question we tackle every week here on Cosmic Origins Revealed. If you love exploring the boundaries of what we can know about life beyond Earth, please take a second to like this video. It truly helps the channel pursue these cosmic mysteries. And now, back to the failed star that changed everything. On October 2, 2025, a research team led by University of California, San Diego professor Adam Burghasser published findings in Science announcing the detection of phosphine in the atmosphere of an ancient brown dwarf known as Wolf 1130c. Brown dwarfs occupy a liminal space in the cosmic taxonomy, too massive to be planets, too small to ignite sustained hydrogen fusion like true stars. Wolf 1130c, 54 light-years distance in Cygnus, is especially unusual. It's older than conventional brown dwarfs and has depleted its sources of heavier elements, including oxygen. Phosphine, a simple molecule with one phosphorus atom bonded to 3 hydrogen atoms, pH3, is notorious. On Earth, phosphine arises naturally from decaying organic material in swamps. And in laboratory settings, only biological processes consistently produce it. This made phosphine a prime biosignature candidate. In 2020, researchers claimed its detection in Venus's clouds, sparking years of controversy about microbial life floating in Venusian sulfuric acid. But here's the paradox. Unlike in previous brown dwarf observations, the JWST data revealed a strong infrared signal from phosphine in Wolf 1130c's atmosphere at about 100 parts per billion, similar to the abundances seen in Jupiter and Saturn. Assistant Professor Eileen Gonzalez from San Francisco State University, who analyzed the spectral data, confirmed that phosphine was present in the expected amount using atmospheric retrieval techniques. The abundance of phosphine in Wolf 1130c is the first time astronomers have found the expected amount of the molecule in a brown dwarf's atmosphere, raising large questions. The mystery isn't that phosphine exists where theory predicted it should. The discovery raises a new question. Why does this particular brown dwarf contain phosphine while others do not? Adam Burghasser stated in the original publication, ironically, Wolf 1130c isn't the problem. It's all the other brown dwarfs and giant exoplanets. Phosphine is the expected molecular form of phosphorus in the low-temperature, hydrogen-rich atmospheres of giant planets and brown dwarfs based on our current understanding of dynamic chemistry. But despite many efforts using ground-based telescopes and JWST, this is the first time we've detected this molecule outside the solar system at its expected abundance. Two hypotheses have emerged. First, Wolf 1130C's unusual metal-depleted chemistry. In normal conditions, phosphorus may be bound in molecules like phosphorus trioxide, but in Wolf 1130C's metal-depleted atmosphere with insufficient oxygen, phosphine can form from abundant hydrogen. Second, Wolf 1130C is part of a triple system that includes a massive white dwarf, Wolf 1130b, which may be a source of phosphorus through runaway nuclear reactions detected as novae.
The implications are stark. Scientists conclude with a simple statement: there is no consistent model that explains the amounts of phosphine we see on Jupiter, Saturn, Wolf 1130c, other brown dwarfs, and exoplanet gas giant atmospheres. Without a better understanding, the use of phosphine as a biosignature is questionable. 124 light-years away in the constellation Leo, the sub-Neptune K2-18b orbits in the habitable zone of a red dwarf star. K2-18b is 8.6 times as massive and 2.6 times as large as Earth. In April 2025, Professor Niku Mathusudan of Cambridge University announced observations suggesting the presence of dimethyl sulfide, DMS, or dimethyl disulfide, DMDS, in K2-18b's atmosphere using JWST's mid-infrared instrument. On Earth, these molecules tell an unambiguous story. DMS is only produced by microbial life, typically marine phytoplankton. It's the compound that gives coastal areas their distinctive smell. The concentrations of DMS and DMDS in K2-18b's atmosphere are very different than on Earth, where they're generally below 1 part per billion by volume. On K2-18b, they're estimated to be thousands of times stronger, over 10 parts per million. The detection methodology relies on transmission spectroscopy. As K2-18b transits in front of its star, JWST can detect a drop in stellar brightness, and a tiny fraction of starlight passes through the planet's atmosphere. The absorption of some starlight leaves imprints in the stellar spectrum that astronomers can piece together to determine constituent gases. Madhusudan's team achieved a 3 sigma level of statistical significance, meaning there is a 0.3% probability that the observations occurred by chance. They used 2 independent JWST instruments, the Near-Infrared Imager and Slitless Spectrograph, NIRIS, and Near-Infrared Spectrograph, NIRISPEC, in 2023, then the MIRI instrument for new 2025 observations. Co-author Mans Holmberg noted it was an independent line of evidence using a different instrument and wavelength range with no overlap with previous observations. But here's where the story fractures. In August 2025, a NASA-led team led by Kevin Stevenson analyzed the same JWST data using independent reduction and retrieval methodologies, demonstrating that the meaty transit spectrum is highly susceptible to unresolved instrumental systematics. Their comprehensive reanalysis found that while the meaty binning scheme adopted by Mathusudan's team favored the presence of DMS and DMDS in K2-18b, 87.5% of retrievals using their preferred meaty binning scheme did not DMDS in K2-18b. The team concluded that red noise, rather than an astrophysical signal, plagues the mid-infrared data, and there is as yet no statistically significant evidence for biosignatures in the atmosphere of K2-18b. Subsequent observations by astronomer Renyu Hu and collaborators published in 2025 found that the planet was rich in water, but that the possible detection of DMS was not statistically significant, and their models found that DMS could be formed there without life. A NASA reanalysis utilizing Bayesian analysis confirmed K2-18b's water-rich atmosphere and presence of methane and carbon dioxide, but the DMS signal, while present, remains below the 5 sigma threshold required for definitive confirmation. The scientific gold standard requires a 5 sigma confidence level, a mere 0.0006% probability that data fits the model by chance. MIT planetary scientist Sarah Sager, who was not involved in the studies, stated, "With thousands of exoplanets in view, the temptation to over-interpret is strong, and when it comes to K2-18b, enthusiasm
enthusiasm is outpacing evidence. The crux of the controversy lies not in the data itself, but what that data means. Can these molecules arise without biology? For phosphine, the answer is demonstrably yes. Phosphine is found in significant quantities in the atmospheres of Jupiter and Saturn, and no one proposes life exists in those planets' clouds. Recent discoveries compound the problem. DMS was recently found in Comet 67P Churyumov-Gerasimenko and in the interstellar medium, environments utterly hostile to life.
For K218b specifically, University of California Riverside astrobiologist Edward Schweiterman noted one reason for skepticism: the anticipated presence of ethane, C2H6, to accompany DMS and DMDS if those gases were present, because UV rays from the star would break apart the molecules into components that would react to form ethane. The absence of ethane suggests something in the models is wrong, or perhaps the DMS-DMDS isn't there. The challenge extends beyond individual molecules. Established inverse methods to interpret observed spectra, already known to be highly averaged representations of intricate 3D atmospheric processes, can lead to disparate interpretations even with JWST's quality of data. A 2021 workshop by NASA-funded programs developed a series of questions to guide discussions and critically interrogate potential biosignatures. Starting with, is the signal statistically significant? The Wolf 1130c discovery illuminates a deeper problem. Our atmospheric chemistry models are incomplete. Scientists state there is no consistent model explaining phosphine amounts on Jupiter, Saturn, Wolf 1130c, other brown dwarfs, and exoplanet gas giant atmospheres, indicating an incomplete understanding of phosphorus chemistry in low-temperature atmospheres. Mark S. Marley, a planetary scientist at the University of Arizona who was not involved in the research, stated that the new data really demonstrates we don't fully understand phosphine chemical networks in the context of atmospheres, so it is premature to rely on phosphine as a biosignature. This ignorance has cascading consequences. If phosphine's presence can't reliably indicate life, what about other proposed biosignatures? MIT's Sarah Sager and colleagues recently published a preprint identifying 15 potential biosignature gases, including chlorofluorocarbons and molecular oxygen, noting the JWST's observations reveal there is no silver bullet biosignature. The statistical bar is extraordinarily high, for good reason. NASA released a statement in April of 2025 reiterating that we would need follow-up studies and multiple converging lines of evidence to confirm true biosignatures and rule out false positives, possibly including independent data from multiple missions and extensive atmospheric modeling. As of November 2025, neither phosphine on Wolf 1130c nor DMS on K218b constitutes proof of extraterrestrial life. What they represent is far more valuable, a recalibration of our search strategy. Burgesser's team plans to test their metal depletion hypothesis through upcoming JWST observations of other metal-poor brown dwarfs to see if the same pattern appears. For K218b, researchers estimate between 16 and 24 hours of follow-up observation time with JWST may help them reach the 5 sigma significance threshold. But the larger lesson transcends individual targets. Laboratory experiments and computational simulations are crucial for interpreting exoplanet atmospheric data, specifically identifying molecules based on their unique infrared light absorption patterns. Researchers emphasize the need for more laboratory experiments to match observed infrared spectra with specific molecules, confirming their identity and abundance. The interplay between observation and controlled experiment defines modern astrochemistry. High-energy ultraviolet photons streaming from host stars can break apart water molecules and initiate a series of reactions, producing unexpected compounds. Identifying a gas in an exoplanet atmosphere resulting from complex photochemistry and verifying its plausibility with models was a spectacular achievement. The most profound shift isn't technological, it's conceptual. We began the JWST era asking, where is the life? The telescope has forced us to ask instead, what even constitutes proof? NASA-funded workshops developed an astrobiology standards of evidence framework with 5 key questions, starting with signal authenticity and progressing through signal attribution, interpretation, and implications. When researchers applied all 5 questions from this framework to K2-18b, they concluded the planet does not yet meet the standards of evidence for life.
This rigor is not pessimism, it's precision. Every uncertain detection teaches us something irreplaceable about atmospheric chemistry under alien conditions. The Phosphine mystery on Wolf 1130c reveals gaps in our understanding of phosphorus behavior in metal-poor environments. The K2-18b controversy exposes how instrumental systematics can masquerade as astrophysical signals. Burgasser stated in his science paper, "Understanding phosphine chemistry and the atmospheres of brown dwarfs where we don't expect life is crucial if we hope to use this molecule in the search for life on terrestrial worlds beyond our solar system. The search for biosignatures is inseparable from understanding our own origins." JWST recently detected complex organic molecules, considered the raw ingredients of life, around a forming star and the Large Magellanic Cloud, a dwarf galaxy 160,000 light-years away. These prebiotic compounds existed in their icy phase, frozen within dust grains before being warmed during later stages of star formation. The Large Magellanic Cloud's lower concentration of heavy elements and intense ultraviolet radiation mimic the conditions of galaxies that existed billions of years ago, providing insight into how complex chemistry might have unfolded in the early universe. If phosphine and dimethyl sulfide can arise through purely chemical pathways we don't yet understand, perhaps the bridge from chemistry to biology is more gradual and more ubiquitous than we imagined. The question is no longer binary, life or no life. It's a spectrum. How much disequilibrium? How many converging lines of evidence? How do we distinguish biology from exotic chemistry we simply haven't modeled yet? We stand at a moment of productive confusion. JWST has the raw power to detect faint molecular signals in exoplanet atmospheres. What it cannot yet do is tell us definitively what those signals mean. A handful of habitable zone planet atmospheres are accessible given the anticipated noise floor, and JWST may continue contributing by designating a planet as a biosignature gas candidate. To do this, we must sufficiently refine our inverse methods and physical models for confidently quantifying specific gas abundances and constraining atmospheric context. The next generation of telescopes, projects like the Habitable Worlds Observatory, still in planning stages, will need spectroscopic resolution and signal-to-noise ratios far exceeding JWST's capabilities. MIT astronomer Eliza Kempton noted that it's an absolute marvel we are able to disentangle signatures of planetary atmospheres from those burning bright stars in the sky. But technology alone won't solve the biosignature problem. We need comprehensive libraries of abiotic pathways. We need high-temperature chemistry experiments under alien atmospheric pressures. We need to understand why phosphine appears where theory says it should, but only once in dozens of observations. The most honest answer to the original question, what if JWST detected the molecule only life can create, is that we don't yet know if such a molecule exists. Life on Earth produces countless chemicals, but none exclusively. Photosynthesis generates oxygen, yet photolysis can split water molecules and build oxygen without cells. Methanogens exhale methane, yet volcanic processes and serpentinization do too. Marine phytoplankton release dimethyl sulfide, yet comets carry it in their icy nuclei.
Perhaps the signature of life isn't a single molecule, but a pattern, an atmospheric cocktail so chemically improbable, maintained in such extreme disequilibrium that no known abiotic process can sustain it. The simultaneous detection of CO2 and CH4 could constitute a disequilibrium biosignature in an anoxic environment, researchers suggested. Context matters as much as content. The Wolf 1130C and K218b discoveries don't close the chapter on biosignatures. They rewrite it, forcing us to confront how little we understand about chemistry under conditions Earth never experienced. This is not failure. This is science at its most essential, finding the edges of our knowledge and pushing beyond them. As we peer into the atmospheres of distant worlds, the molecules staring back at us don't just ask, "Is there life?" They demand, "Do you even know what you're looking for?" And that uncertainty, that productive confusion, is exactly where discovery begins.